So in this video, we want to discuss chemical bonding, the three major types of bonding, which are metallic, ionic, and covalent bonding. So with metallic bonds, these are bonds that exist between metals only, either pure metals or alloys. And what you end up with in a metallic bond is closely packed cations. Cations are positive ions. And those positive cations are surrounded by free-floating valence electrons. So you have these electrons here in here that are free to move. And so that ability to move around, we often call this a sea of electrons. This ability of the electrons to move are what gives metals much of their characteristics. They're good conductors of electricity because the electrons are free to move. We end up having ductility, something that's ductile, remember, or ductile is capable of being drawn into a thin wire. And if it's malleable, so two characteristics of a metal, they're capable of being hammered into thin sheets. So as you hammer and stretch these metals, the electrons move around and they keep cushioning, or these electrons move around and keep cushioning those metal cations so that they don't come in contact with each other. Because they don't want to come in contact with each other if something happens and they get too close to each other, they're going to repel because they're positively charged. So the electrons cushion the metal cations, keep them from coming in contact with one another. If you bend it too quickly or you have a sharp blow that occurs very quickly and you don't give those electrons time to move around, that's when you can cause a metal to shatter because you will have those positive cations come in contact with each other and repel. So that's a metallic bond. Ionic bonds are bonds that are formed when electrons are transferred. That's the key word, transferred between atoms. And these atoms have big electronegativity differences. Now, electronegativity is just a measure of how strongly they're holding on to their electrons. Some atoms hold on to electrons very strongly. Those are the ones that would like to gain electrons. And so the ones they already have, they're going to hold on to really strongly. Now, if on the other hand, they want to lose electrons to reach that stable state, like our positive or our metals that want to lose electrons, they're not going to hang on to their electrons very strongly, and so their electronegativity is not going to be very high. When you have that big difference of something that wants to gain electrons and something that wants to lose electrons, they tend to bond together. Take, for instance, sodium and chlorine. We've got sodium, and if you remember sodium's in group 1A, and 1A elements want to lose one electron. They have one valence electron, so they would like to lose that electron. Chlorine, which is over there in group 7A, has 7 valence electrons. Chlorine would very much like to gain one electron. So if you get sodium and chlorine too close together in the same container, then that's exactly what's going to happen. That electron on sodium is going to be grabbed by chlorine. Sodium didn't want it that badly anyway. And so what we end up with then is a situation where sodium has lost an electron, so it's now positively charged. Chlorine has gained an electron, so now it's negatively charged. If they were close enough to transfer electrons in the first place, then now those opposite charges are definitely going to attract. And that's when we form that ionic bond. But what happens, those ions, one more thing, the ions are held together in structures that are a lattice type structure. So you don't have molecules in an ionic compound. You have a lattice structure. We've discussed this before on a previous set of notes, that we have this alternating positive and negative charges. There are different kinds of lattice structures. This just happens to be one for sodium chloride. But again, there are no individual molecules. A covalent bond is a bond that's formed when two atoms that have a similar electronegativity value, they're usually nonmetals, share one or more pairs of electrons. And the reason they do this is because, think about it, if you've got two fluorines, both of the fluorines are in group 7A. They both want to gain an electron. Neither one is going to be willing to give up an electron. So the only option they have in this tug of war is if they share. And that's exactly what they do. They share a pair of electrons, and you end up with a covalent compound. Covalent, cooperate, share, and that's the type of bond that results in molecules. When you have, for instance, an oxygen share a pair of electrons with two different hydrogens, you get water molecules. Very much different in structure from the ionic lattice structure we saw just a moment ago. So those individual molecules are created when we have covalent bonding. Now, we'll spend a whole class period talking about covalent bonding, but the last thing I want to do is just to show you how one way to write a Lewis structure for an ionic compound. The first thing that you want to do for these is to draw their Lewis structure for each individual element. So sodium chloride is made up of sodium. Sodium has one valence electron. It's in group 1A, so it's going to look like this. Chloride is the ending name for chlorine. We talked about the names for our negative ions in the previous set of notes, in the previous video. Chlorine is in group 7A, so it's going to have 7 valence electrons, so it's going to look like this. And so what's going to happen is that sodium, which wants to lose an electron, is going to give that electron away to chlorine. And the way that your textbook wants this particular type of structure drawn is to show that now sodium is positive. The negative one we're going to put in brackets, and it now has its 8 valence electrons, and it's going to be negatively charged. So that's what we want that final structure to look like. Barium iodide, on the other hand, barium's in group 2A, so it's going to look like this. Iodide is the ion name for iodine, and iodine's in group 7A, and it's going to look like this. So barium wants to give an electron away, and iodine has enough room to take one, but that's all the room it has. So what are we going to need? We're going to need another iodine. So draw in another iodine to show a place for the other electron from barium to go. So what does this result in? It results in a situation where barium, since it lost 2 electrons, is going to be Ba2+. But we have 2 of our iodines. We're going to draw it like this. That now have 8 valence electrons each and that negative charge. So those 2 negative charges and the 2 positive charges from barium are going to balance each other out in a compound. We'll talk more about that later. Potassium nitride. Potassium is in group 1A. It has 1 valence electron. Nitride is the ending name for nitrogen. In group 5A, it's going to have 5 valence electrons. Sodium's going to give away one of its electrons. And that makes, I said sodium, I meant potassium. Potassium gives away one of its electrons. That makes nitrogen very happy. Well, it makes potassium very happy, but nitrogen not so much because it's still got 2 open places. So how are we going to get that situation to work out? Well, we need another potassium with a valence electron, and that one's going to be able to join up with this electron and have a pair of electrons. It's going to give that away. And then Another potassium we're going to need, and this potassium is going to be able to give away its electron to nitrogen. So it looks like it takes 3 potassiums to give up enough electrons to make nitrogen happy. So how are we going to write that? We're going to show that we have those 3 potassiums with the positive 1 charge because they lost an electron. We only have 1 nitrogen, so that nitrogen, remember that the negative ones are going to go in brackets. But now that it's gained 3 electrons, what's its charge going to be? It's going to be a 3 minus. So your positives and negatives better balance out on these in order for you to have a correct formula for them. So again, this is the boxed in answer for this one. This is the answer for this one. Finally, let's look at one more. Well, I guess we've got 2 more examples. We've got aluminum bromide. Aluminum has 3 valence electrons. Bromide is the ending name for bromine, so it's got 7. So aluminum wants to give away 3 electrons, so one of them can go to bromine, but that's not enough bromines because we need some more places for aluminum to be able to give away an electron. So let's put another bromine up here. We can get another electron taken care of. Looks like we're going to need a final bromine in order to take care of that final electron that aluminum wants to give away. So it's all about matching up the electrons that want to be lost with the electrons in species that want to gain electrons. So now we have 1 aluminum, and that aluminum, now think about it, it just lost those 3 electrons, so it's going to be a 3 plus. We now have 3 bromines. Each one of those bromines gained an electron. So the bromine itself is just negative, but there are 3 of them, so it balances out the 3 positives for aluminum. Remember, the charge outside that bracket is for just the single ion that's inside the bracket. Finally, barium phosphide. If you can do this one, you can do any of them. We've got barium. Barium has 2 valence electrons. Phosphide is the ending name for phosphorus. It's in group 5A, so it has 5 valence electrons, so it's going to look like this. So phosphorus wants to gain 3, barium wants to lose 2. Might be a little more complex. There goes barium, one of barium's electrons, and here's another electron. So we've given away 2 of barium's electrons, but phosphorus still isn't happy because it's still got a place to bond. So let's get another barium with 2 electrons, and we'll take care of phosphorus. So all 3 of phosphorus's electrons, it's gained all the 3 that it wants, but now barium, we've still got this barium over here that's got this free electron that it wants to give away. Looks like we're going to need another phosphorus. So I put in another phosphorus here, which is going to give a nice place for barium to give away its electron, but now this phosphorus still has 2 electrons that it wants to gain. So what are we going to need? 1 more barium should do the trick, so that one of these electrons can be given away to phosphorus, and so can the other one. And now everything is lost electrons that wants to lose electrons. Everything is gained electrons that want to gain electrons. Looks like we've got 3 bariums to put in this Lewis structure, and looks like we've got 2 phosphoruses. So our bariums are going to be our positive ones. So we're going to have barium, and each of the bariums are 2 plus. How many of them are there? 3 of them. So we've taken care of our positive ones. Now phosphorus, each of the phosphoruses gained 3 electrons, I didn't do a very good job writing those dots, but I think you can see what it's supposed to be. And when it gained 3 electrons, each of those phosphoruses became a 3 negative. But how many of them are there? There are 2. Double check yourself by looking at what your charges add up to be. You've got 3 times the positive 2 here, so that's 6 positives. You've got 2 times the negative 3 here. There's 6 negatives. So it looks like you've done a nice job of balancing out those charges. So that's going to be the answer for this one. So that's what you're going to be asked to do on part of your assignment for today.